Welcome everyone. Thank you very much for joining another edition of this EEG Data Science Distinguished webinar. Before presenting our speaker today, let me briefly go over some logistics like every time. If you have any questions, you can write them there in the Q&A chat, and towards the end of the talk, we're going to select some of those to be answered by our speaker. During the talk, I also monitor the Q&A in case there is any pressing clarification question that makes sense to address in the middle of the talk. Otherwise, we're going to address most of them at the end. The talk will also be recorded and uploaded to our YouTube channel for future access. So that being said, it is my pleasure to present today Professor Alfred O as our distinguished speaker for the data science seminar. Professor O obtained his PhD in EE from Princeton in 1984. At that point, he joined the University of Michigan, institution in which he has been for over 36 years now, so it's impressive. Of course, he started as an assistant professor, then associate, then full professor in ECS since the year 2000. He's also the John H. Holland Distinguished University Professor of Electrical Engineering and Computer Science, and the R. Jamison and Betty Williams Professor of Engineering. He was also a founding co-director of the University of Michigan Institute for Data Science, the MIDAS Institute, a very interesting initiative. His recent research interests are in high-dimensional spatial-temporal data, multimodal data integration, statistical signal processing, and machine learning. Professor O has received plenty of recognitions for his work, so just handpicking a few here. The IEEE Signal Processing Society Technical Achievement Award in 2013, the 2015 Society Award, also by SPS, and the 2020 Fourier Award from the IEEE, among many other recognitions to his research, teaching, and service. He's a fellow of SIAM and IEEE, where he has been very active, serving in the past as president of the IEEE Signal Processing Society and as a member of the IEEE Board of Directors. On a personal note, I've been following Professor O's work since I was a first-year PhD student back at Penn. He has worked on plenty of graphs and network-related problems, analysis of multi-layer graphs, clustering, graphical models, network inference, growth models on graphs, now some graph neural networks, you name it. He has always been someone to look up to as someone doing cool network stuff within the Signal Processing Society, which is also my home society within IEEE. So Al, thank you very much for agreeing to spend the afternoon with us today. It is a pleasure to have you here, and the floor is all yours.
Great.
Perfect.
Well, thank you, Santiago, for that very kind introduction. I'm really happy to be able to talk about some of the work that we've been doing in very high dimensional multi-way data and coming up with ways to computationally feasibly and with interpretability be able to pull insights from such data. It's been certainly a while since I've been to Rice. We were talking earlier, Santiago and I think it's probably been about 15 years or so. I would have enjoyed coming and being there in person and enjoying the company of many friends that I have at Rice over many years. I'm also hopefully this is not a perfect medium to be addressing a group all over the country and maybe all over the world. Through the internet. Yesterday we had a 4-hour power outage, so I hope we don't get that again during my talk here. I don't think so, but you never know. I think that these power outages are probably renewable processes, so we can't take much comfort in that. I'll be talking today about these ultra-sparse models for multi-way data, and I'll talk first about some of the background in multi-way data representations with some examples to motivate why we're interested in this problem, and in particular, framing the problem as a problem for second-order analysis as opposed to first-order analysis, which is where most of the multi-way data representation work has occurred. A lot of it in the applied math community, tensor representations and so forth. That here we're focusing on the statistical aspect of learning multi-way data representations for second order covariance and inverse covariance techniques that are associated with that. So, and then I'm going to talk about Kronedker-product as a particular multi-way representation that goes back many years, leading into tensor graphical lasso, the Tera Lasso, and then something we're calling the Sylvester graphical lasso. And then I'll finish with an application that sort of illustrates these decomposition methods and models for multi-way covariance analysis. So if you're interested in any further details, you can go to some of the references that I'm showing here. This also, by way of convenience, allows me to acknowledge at least some of the collaborators and students who have contributed to this work over the past 8-9 years. And in particular, Yu Wang, Wayne Wang, number 4, is probably listening to the seminar, and so he can raise his hand if he doesn't agree with something I'm saying, and he'll be right. So I want Santiago to interrupt me if that happens. So learning multi-way data is effectively a problem in finding some way to represent in a lower dimensional space or fewer parameters a multimodal data cube. Modal referring to different dimensions. So in, say, gene expression analysis, the dimensions might correspond to different times at which samples were taken, different gene expression levels that were associated with those times, and maybe different conditions, right, under which the samples were taken. So, 3-way for that case. And so D1 through D3, in that case for time, gene, and phenotype, would correspond to the individual modal dimensions, and of course the overall dimension is the product, right, of those 3, which could be very, very large. And we associate another number that is going to come up later on, which is the dimension as seen from the kth mode, which is basically the total dimension divided by the dimensions that the kth mode sees, and that's going to turn into an improvement factor that one can obtain using a Tera Lasso as opposed to a graphical lasso representation of the inverse covariance. So common traits of these data cubes and a k-way tensor like Z is that, as I say, we have different modes, mode types. We may have different numbers of dimensions, and it may be that the data cube is sparse, or maybe the moments are sparse. Maybe the mean or the covariance or some other higher order moments of the entries or cross products of the entries may be sparse, telling us that there's a limited amount of dependency, right, between the modes or within one mode, between the variates, the covariates. And so in this situation, the data cube should have hopefully a sparse and low dimensional approximation. If not, we're kind of up the creek, because these can be enormous, millions or hundreds of millions of entries. As I was saying in my intro, the first order representation approach is to try to kind of model the mean. So you might have replicates from the gene expression study, let's say, and you then would say try to model the sample mean in this way as a vector product, outer product, a Kronedker-product, which is here, or what we're talking about in the Tera Lasso, so-called Kronedker sum product, where Kronedker sum decomposition. Second order representations, which is the topic of the talk, is to look at the covariance, so the dependency structures between these modal covariates, and represent them as different products, inheriting, of course, the dimensions that one started with in the data itself, and so that then translate into the order of the number of products, or I should say the number of Kronecker products that you would see in this representation, corresponding to 1 minus the dimension. So an application where this comes up is, which is well known in radar, is in space-time adaptive processing, where you have, in this case, a two-way data cube of a range and azimuth or angle of the radar, which is an acquisition of a volume of space, of radar cross sections of objects in space. So this then gets decomposed. There could be clutter at different ranges that is maybe slowly varying over range, but maybe stationary within a given range. And so one can then, if there are targets present in a region of that range slice, you can form a covariance matrix to estimate the clutter and then basically normalize it out and clean up the image so that you emphasize the objects that are generating bona fide coherent cross-section returns. So estimating the covariance is important in this case, but the number of covariates could be huge, and you might have, again, slowly varying covariance and dependencies across both the azimuth and the range, and so therefore one can come up against a very high dimensional problem when you talk about estimating covariances when you have high dimensional images, right? So lots of pixels in range and azimuth across ranges is sometimes called. And this is just an example of what I just said, which we applied this Kronecker decomposition method in order to clean up the reference image on the left at a particular, this is just a particular cross range, and pulled out these target trajectories after applying this covariance decomposition estimate to the clutter covariance. Another example is gene expression that I was mentioning a minute ago. And in this case, we have on the order of 3,000 by 30 by 100, 9 million entries, and in the matrix, right? 3,000 genes, 30 time points, and maybe 100 subjects or samples. And so huge matrix, we want to extract, say, temporal behavior from this, let's say the samples were measured over time. So we have these 30 time samples. And so in this case, we applied, again, this Kronecker method, Kronedker-product method, to decompose the gene and time into a 3,000 by 3,000 inverse covariance estimate and a 30 by 30 temporal covariance estimate. And then what comes out is the temporal estimate yields immediately through these factors, through a PCA, the cyclical circadian rhythms that were hidden in the data. So it kind of condenses down, distills down these dimensions in a very simple manner, just through a factorization of the inverse covariance. So what's going on? So the covariance representation is simply in a case where we have a data array with D1 by D1 D2, so a two-dimensional array, one epoch, one sample. If you vectorize that, you get a D1 by D2 vector. You look at the covariance associated with that the covariance matrix. It's a D by D covariance, which is blocked out here in the terms of the patterning of that matrix. Different blocks of dimension D1 by D2 are going to be associated with, in the case of time, let's say, where we have time and gene, let's say, on the D1 and D2 domain, will correspond to correlations across time within a gene. So one D1 by D2 block, let's say right here, corresponds to these correlations between genes at delayed or lagged relative to 2 time points, or three successive time points. So this patterning is important because this is what leads to the insight into the decomposition, where a Kronedker-product decomposition is basically going to reduce to an assumption that the gene-to-gene correlation is effectively just constant. So you have a single matrix that corresponds to each one of these blocks, but with a scale factor that corresponds to a temporal correlation that scales each one of those constant matrices. So a little bit of math now that we have to sort of dive into what these covariance decompositions correspond to. We have a D by N measurement matrix, N being the number of samples assumed to be independent, identically distributed, so that you can construct sample covariances in a homogeneous fashion. We'll call this Z, or Z matrix. If you vectorize it, you get a covariance matrix, sigma, and you can then form a sample covariance estimate by D by projection of a outer product after projecting out the mean, and that gives you then a sample empirical covariance that can then be modeled in terms of a likelihood. And so in this case, the matrix normal model for this data array Z is in a Gaussian multivariate distribution with, in the case of an unconstrained or unstructured covariance, a function of the inverse covariance. And so this is going to be the objective of this multi-way decomposition, where one will try to apply different models or form decompositions into Kronecker sums, Kronecker products, etc., to simplify the inference of these covariance matrices, or actually we're going to talk about inference on the inverse covariance, the natural parameterization of the multivariate normal family. And this will lead to trying to identify or estimate on the order of D squared unknown parameters, which is a lot of parameters, especially if D starts out being 9 million, right? So if you want to have if you want to be able to solve this maximization problem of maximum likelihood, maximum log likelihood, then you have to have number of samples exceeding D, linearly in D, just so that you have an invertible sample covariance. And it needs to really be on the order of D squared to get reasonable performance in terms of, say, the mean Frobenius norm error in estimating the covariance with sigma hat. So if you have more structure, like sparsity, you can reduce the requirements and obtain an error that decays as order D over n as opposed to order D. So you only need n on the order of D as opposed to n on the order of D squared samples, right, in order to accurately estimate the covariance or inverse covariance. And that can be implemented using the graphical lasso, which simply applies a relaxation of the sparsity constraint on the inverse covariance to this multivariate normal log likelihood. So this penalized maximum likelihood estimator then is can be generalized to penalties what I call P of omega, which can be designed either for sparsity or for shrinkage or for other types of structure like Copeland structure or Hadamard-Hankel structure. You can induce Gaussian graphical model structure by looking at sparsity, where the sparsity pattern guarantees certain fidelity to the model. You can look at sparsity in the covariance, sparsity in the inverse covariance. They're not equivalent, of course, unless your covariates somehow block together into groups that are codependent, but are interdependent between blocks. And in that case, sparsity models would be the same for the inverse or the covariance itself, in terms of connections between those blocks viewed as edges in a graphical model, that is, dependencies between blocks. So we're, as I say, going to focus on the sparse inverse correlation as opposed to the sparse correlation for most of this this talk, since as we're going to see, it's much more closely related to generative models, which is going to play a major role in the discussion of the Sylvester graphical lasso, generative models with a stochastic representation. Okay, so Kronecker products then, a Kronecker product representation of the inverse covariance or of the covariance has the structure that I just explained in words, showing that pattern matrix a minute ago, right? Where you're assuming that, you know, the gene or call it the spatial component of this time-space covariance is basically repeated over these blocks with a single scalar, which corresponds to the temporal correlation, right, between different time points. And so this Kronecker product structure is very natural, very simple. Obviously has some drawbacks of introducing a lot of redundancy and injecting B everywhere you see, right, in terms of all time points, all time lag points, I should say. But the Kronecker product has some really nice properties from the point of view of analysis, which allows one to obtain algorithms and good asymptotic properties for maximum likelihood, penalized maximum likelihood sparse regularized maximum likelihood estimates of A and B. So these are very, very well-known properties, which you inherit positive definiteness into the Kronecker product. You inherit invertibility. Determinants are easily calculated, and there's a nice least squares through reformatting of the dimensions that allows you to formulate least squares as basically a rank 1 fitting problem. So there's also a stochastic representation, which I mean there is a stochastic model, a generative model, where if you start with omega, some arbitrary omega, which has this form of A Kronecker B, then you can generate any Z with that inverse covariance by taking a matrix which is isotropically random, W, with IID entries. P and Q here are D1 and D2. Sorry to change notation. And then pre and post multiplying, say, the time and the space domain of this W matrix by square root factors of the inverse of A and B, respectively. So it's a stochastic representation in the sense that you could describe Z as having provenance, as coming from a sort of canonically uncorrelated, independent, latent covariate W. And this is important in terms of both interpretation and also in terms of building on the model or building generative models from a Bayesian viewpoint. And we'll see this is not the case for the Tera Lasso, which will lead to why we were interested in Sig Lasso. One interpretation of these Kronecker product models, which is physical, gives some physical intuition, maybe more so for people in communications and signal processing than in statistics and other fields, is this physical example where you have two signals generated from noises, isotropic white noises over time at two different locations in space, and these signals are emitted and propagate to an array of measurements, antennas or acoustic sensors or light sensors or what have you. And so what's received, oops, sorry about this, what is received is a convolution, like, or a sum of attenuation coefficients over the medium which are now anchored at each one of the spatial locations U of these elements, these sensors, weighting the different signals that have been generated here. I'm assuming S signals, S equals 2 in this picture. So we have a convolution on the right and on the left of what's essentially an isotropic noise process. And so you can define, or you can describe this precisely as this sort of stochastic representation, which will have a Kronecker product covariance and inverse covariance structure. So there are very natural physical processes which will obey this type of Kronecker product structure, such as the one I'm showing here. And so just to get a feel for the advantage of these Kronecker products, just in terms of the reduction of the number of parameters, if you have an 18 by 18 covariance matrix, 153 unknown cross correlation parameters, and you describe that by a 3 by 3 times a 6 by 6 Kronecker product, you've reduced the number of parameters to 3 plus 15, right? So you've gone from 153 to 18 parameters. If you apply sparsity in addition to that, you can go down to 7 overall parameters from 150. There's a very significant savings in bookkeeping, and also in the estimation error performance, mean squared error decay rates that occurs by incorporating these types of assumptions. Of course, the assumptions need to be verified in the data for have an unbiased estimate in the end. In terms of the sparse incorporating sparsity, it's very natural in this setting of the Kronecker product model, because you simply have to take the normal matrix normal objective function and then penalize on the sparsity of each one of the Kronecker factors. So the lambda A and lambda B are regularization parameters, non-negative, and you tune those cross-validation or using other tools for model order selection, and tuning up lambda A and lambda B will effectively incorporate more and more sparsity into the Kronecker product model. Tera Lasso takes a tack that says the main issue in Kronecker product methods of Kronecker G-Lasso is the lack of convexity of the optimization problem, and its tendency to inflate the number of edges in the associated dependency graphical model. So lots of high dependencies, not non-zeros in a graphical model, which I'll give you an example of in a minute. And so this Kronecker sum is what forms the basis for the Tera Lasso instead of the Kronecker product. And what's nice about the Kronecker sum is that, unlike the Kronecker product, it's linear in the A and B Kronecker factors. So that means if you model the inverse covariance with a Kronecker sum, you effectively have turned a problem which is a bilinear problem in the trace to a problem which is linear, and have converted the determinant into a convex quantity. So you basically now have a convex optimization. The tensor graphical lasso effectively allows you to go to a k-way Kronecker sum representation of the inverse covariance. And the Kronecker sums don't have such nice properties as Kronecker products, but they do have, linearity, associativity, some strange distributivity properties. There's no simple eigendecomposition property. It may not be, that amenable to interpretation. But this is an example of shows sort of the difference between the Kronecker sum and the Kronecker product for a fixed set of. Here we have a three-way problem. So these graphs correspond to a 4 by 4 4x4 and 2x2 covariance or inverse covariance matrix that correspond the vertices to rows and columns of that matrix, and the edges are entries, that is pairs of rows and columns for which that entry is non-zero, right? So this encapsulates the sparsity of these three components. Of course, this one is non-sparse; it's full because there are only two elements, and they do have an edge. And so, if you look at the Kronedker product, you have this looking at from the point of view of one node. Who else is it connected to in the three-way representation? The Kronedker product, you get a lot of injection of this B matrix here, right, into all the other dimensions, because B is being replicated everywhere in that patterned matrix I was showing before. Whereas in the Kronedker sum, you don't have as much propagation of these edges. So it's a more parsimonious for a fixed number of edges or fixed sparsity in the component multi-way components. It gives you a more parsimonious description of the full covariance matrix, the Kronedker sum in this case, than would be for the Kronedker product. So there's this parsimony that comes with it as an advantage, and there's that convexity of the objective function that allows one to apply convergent convex optimization algorithms. And so the Tera Lasso estimator is the inverse covariance estimator, which effectively optimizes over this restricted space, a cone of Kronedker sum matrices that are such that their resultant omega is positive definite, and the optimization penalizes for sparsity on individual multi-way components with a regularization parameter rho k for the kth mode, and mk is a weighting parameter to sort of equalize the effect of each one of these components, so that rho k sort of becomes dimensionless or less sensitive, if you like, to different amounts of different numbers of covariates per dimension. And so this then gives a objective function which is convex in these Kronedker sum components. And so one has at our sort of disposal lots of convex optimization methods that you can choose from. We selected a method, Tabul and Beck method of iterative thresholding that we call it the TG-ISTA, Tera Lasso ISTA, and it converges quite quickly. One can also get theoretical results on convergence, statistical convergence in Frobenius norm. That's missing here from the convergence from the norm. So you make some standard assumptions of sparsity, and that the eigenvalues don't either blow up or aren't equal to zero, and then you can get an error bound under certain conditions, which specify the rates at which you need to increase the regularization as the dimension increases, the total dimension of the problem increases, and that should be 1 over dk, not over k. And then with a certain probability, sort of the standard concentration types of results. So a certain probability, overwhelmingly close to 1, the actual Frobenius norm error in the estimate relative to the truth of the inverse covariance, it behaves in this way. And so the important thing to note, I'm not going to go through all the interpretation or the math here, but that it increases in D, and it increases in the amount of non-sparsity S, increases in the number of multi-way components, It increases as your minimum eigenvalue gets small. All these are natural things if you're trying to estimate inverse covariances or high-dimensional sparse quantities. But the important thing is that it also can be compared head-on to the G-Lasso, where you're not imposing this kind of Kronecker sum. Instead of it's just the ordinary G-Lasso, where you have the full rates, the full covariance, I should say, model. And we have a factor which is min k over mk, which is sort of the minimum dimension as seen from the kth mode of the remaining dimensions, so the codimension relative to the kth mode. The minimum of that codimension is an attenuation factor that improves the convergence rate. So it's remarkable that implies that if you have a problem with a lot of different modes, and some of those modes have a minimum which is sufficiently large, you get a very significant improvement on the rate of convergence as a function of the dimension, right? Or as a function of, for Higgs dimension, a function of the number of samples n. So how about in practice? So the Tera Lasso, we have runtime comparison this is for various k-way Erdös-Renyi graphical models where you choose the edges at random and then project onto the positive cone to get a valid inverse covariance matrix with various dimensions of p is actually d here, and various dimensions dk and 10 samples throughout. And so what you can see is that with Tera Lasso, because of its convexity and because of its the simple decomposition, linear decomposition in the inverse covariance, we're able to scale this to billions of variables, and with runtimes which are reasonable. This runtimes were actually computed several years ago that correspond to unachievable with the previous methods. Big Lasso is Shuang Zhao, who's a co-author on this paper, the GRSSB paper where this work is presented. This was her original work on the bigraphical lasso, which K was 2. So the scalability of Tera Lasso is very, very attractive. And computationally, you get a reduction of floating point operations from a product of the third power of these dimensions to a sum. So the third power comes in because you have to do matrix inversions in the set, but not of the entire matrix as you do in G-Lasso. In the Tera Lasso, you can get away with doing matrix inversions of only kth mode, as you can with Kronecker product methods. We also applied this to a kind of a fun data set from the National Center for Environmental Prediction from NOAA, where satellite data has been formatted so that they give you a grid of over 10,000 points over the globe, measuring things like wind velocity, barometric pressure, and a whole bunch of other things at various elevations. So we took one of those elevations and we looked at the western part of the US and the eastern grid of the US. This is a grid, 10 by 20 grid over time, so over a certain time period. And what we're going to do is we're going to apply this Tera Lasso to try and describe differences between the western and the eastern grid in terms of the dependency structure that's encoded in the inverse covariance with relatively few samples. And so this is the results of applying this Tera Lasso method, where I show the latitude factor, the longitude factor. What I'm not showing here is the third dimension, which is time. So we have a k equals 3 model here. I'm not showing that dimension, but I'm showing the latitude, longitude for both the eastern and western US, along with the corresponding graphical model. What you can note here is that the graphical model for the western US has this, break here, and this goes from east to west, and so this break actually corresponds to a break in the dependency structure, which occurs right around Breckenridge, Colorado, which I was talking to Benham a few minutes ago about. So it's the Rockies that create this this dichotomy between, if you like, wind velocities and weather to the east and west. So natural sort of confirmation, if you like, that we can pick at least that level of meteorological ground truth out from this data. And this just shows comparisons in terms of a Tera Lasso, G Lasso, Kronecker sum, Kronedker-product, different Kronecker sum method that I'm not discussing here. But the point that I want to make with this is that for the eastern grid, that you can recover with basically one snapshot, because of the fact that the weather system is so, if you like, homogeneous, stationary over space. With one snapshot, you can pull out, because of the Kronecker sum regular structure in the covariance, the equivalent covariance that would take you 50 snapshots if you use a standard shrinkage estimate. So, we've dropped by more than a factor of 10 the requirements on the number of samples to get to sort of the basic pattern of the covariance. Now, of course, a Tera Lasso Kronecker sum may not be a perfect model. It might have some bias relative to the actual inverse covariance, which the shrinkage estimate does not have. But we can see, at least from the structure of these inverse estimates, that the covariance estimates, that we can recapitulate a large part of that structure, which comes back in the Tera Lasso estimate after 50 iterations, but a much cleaner estimate, as you can see, than the ordinary shrinkage estimate using the standard covariance matrix without any structure. Right. So in the interest of time, I'm going to skip the use of these covariance estimates, Tera Lasso covariance estimates, to actually do prediction. And we're not talking about replacing the Weather Channel meteorologist tool with Tera Lasso. Talking about prediction at a coarser scale of predicting seasons. So I won't go into that. I'll just jump into Sig Lasso. And so the motivation here is that the stochastic representation of Kronedker Lasso is very nice, but there is no such natural representation, at least that we could think of, for the Kronecker sum representation of the inverse covariance. So Tera Lasso has these really nice properties in terms of inducing convexity and being linear in the factors in terms of the inverse covariance, but it doesn't have this generative model representation where you can talk about starting from a latent variable and apply some very natural functions of the Kronecker factors to pull out the structure of the actual measured process that has a Kronecker sum inverse covariance structure. So the Sig Lasso is an innovation that introduces interpretability, a generative model, a stochastic representation into the covariance, inverse covariance representation. And so we start by looking at sort of the broadest class of physical processes that one might naturally be attracted to, which are functions that satisfy some sort of partial differential equation. So a physical process might be a function u, which if you sample that over the domain, you get your function z that we've been describing before, that corresponds to the data. And so a partial differential equation, script d is some differential operator There's a boundary gamma on this domain, and there's this boundary here is, and there's it has to be 0 on that boundary. So these are the natural generating process. F is a say a Wiener process, so like W that we defined before, isotropic process. We have this differential operator, which choose it as various types of operators. You can get, heat equations and Navier-Stokes equations and equations that can describe lots of physical processes in fluid dynamics, weather, heat transfer, and so forth. This is a generative forward model, and there are lots of numerical solvers that solve these models using finite difference or finite element methods. And if you sample this by discretization that these methods do, then you turn this partial differential equation description, this stochastic representation of U, but implicit as opposed to being explicit, where you had what we had before the product, right, of GWH times U or times F, excuse me, leading to U. This is an implicit equation for U, which is down here after discretization, right? So we have now U described through this differential discretized operator U, and we have an equivalence. We can now talk about different types of grids. There's a nearest neighbor property to these grids, a local data passage property, a local dependency property, conditional dependencies of U at one grid location is equal to 0 in all other grid location relative to all other grid locations except for its nearest neighbors, right? Because of the physical nature of this partial differential equation description. So this partial differential operator script B gives us a sparse matrix B because of this nearest neighbor exclusive conditional dependency. And it turns out that D has Kronecker sum structure. And this has been well known for many years, 40 years, in the numerical differential equation solving community. And so if the covariance of this right-hand side, B, which is this discretization of F, is isotropic, so sigma squared I, then the inverse covariance has a sparse square root factor. And that we can look at from the perspective of elliptical equation, the Poisson equation. Let's just get down into the weeds here a little bit, but this just shows how at one particular location, in this case in space, X and Y are spatial variables, that the U process, what we're calling Z, only depends upon the other location process samples through the nearest neighbors, through the grid. This is a square grid in this case. And so this B immediately you can identify as this tri-diagonal discretized Laplacian. We end up with a Kronecker sum representation. B Kronecker B U equals B. The inverse covariance is then equal to this, and we have this Kronecker structured U. So just shows on an Euler grid. The Sylvester Glasso is basically equivalent to defining this matrix of white noises, of isotropic noises W, and saying that the multi-way matrix, the measurement matrix, is related implicitly to W through this Sylvester equation, where you have A applied state of time on the left, B applied to space on the right, and so AZ plus ZB is equal to W. So that describes a very wide class of discretized partial differential equation generative models or forward models driven by these canonical isotropic noises. And so you can go through the math, but under this Sylvester equation representation, vectorizing it, you have a Kronecker sum representation for the vectorized Z and vectorized W, where that's the Kronecker sum is what we described before. And so if you then model the inverse covariance with this Kronecker sum, that should be a sum, that's a typo, then you get this Sig Lasso representation where the inverse covariance has this Kronecker sum squared, right? Because of the fact that this is a Kronecker sum operation on the covariates. So the covariance of those covariates is going to involve the Kronecker sum squared. And we have this stochastic representation. So that's in a nutshell the model. So you're modeling the inverse covariance by the square of a Kronecker sum, as opposed to a Kronecker sum itself. And the reason that we propose doing this is because this leads to a generative model with a stochastic representation that's very widely applicable to lots of different physical processes. And so we can now write down the Sig Lasso as just an optimization. So I'm not going to belabor this. It's just an optimization now with a square here as opposed to the Tera Lasso. And so that does present some challenges in terms of optimization. It's still convex, but it's not as simple to implement as a Tera Lasso, where you have this linearity. Now we have quadratic dependence, right, on the factors in terms of the log likelihood. But we have a method that's described in the AI stats paper that's coming out this year that's related to the Buehlen-Meinshausen approach of residual, computing residuals using a lasso type of, the residuals of lasso predictors using various components, pairs of components in your multi-way, in this case a two-way case, similar to the method Kare and Rajaratnam's method Concord, and also the space method, Peng space method, which I'm not going to describe. We do have a theorem which gives us again a description of how one might choose these regularization parameters as a function of the dimension and as a function of the number of samples in order to guarantee that you get the convergence rate in terms of estimation accuracy, estimation consistency, and also sign consistency, so that you're extracting the right signs of the entries in the inverse covariance, or in the A and B Kronecker sum components. So one can therefore relate the choice of the regularization parameter to guarantee that you get consistent estimates. Beta is just here the amalgam of all the unknown parameters in the problem. Right. So I'm going to finish off on an example. This is just a simulation example for a very simple case showing the difference between a Kronedker product, Kronedker sum, and the Sig Lasso gives you a kind of a compromise between the Kronedker product and Kronedker sum, which achieves this stochastic generative model interpretation. And so it's a compromise, because if you square the Kronedker sum, you're going to get products, right? And so you're looking, in the end, you have sort of this mix of two models. And this just shows some, Sig Lasso is, when applied to structures that aren't Kronedker sum, but are rather Kronedker product, or Kronedker sum not squared, right? That the Sig Lasso, in terms of the peak, the Matthews correlation coefficient, in terms of false positive and true positives, detecting or recovering the sparsity structure of the inverse covariance, is not doing too badly. It's, of course, different regularization parameters, than the matched case here, right? So, for example, for the Kronecker sum, not squared, you get almost as high Matthews correlation coefficient using a Lasso model, a mismatch model, as you would if you use the true model, which is, in this case, the Kronecker sum. And then I'll just finish off on an application, which is a data set that it was extracted from a alcoholism study that is performed on subjects using EEG. There are 77 alcoholic subjects, 45 control, and there's a stimulation that occurs periodically that one then looks at the evoked potential response in this study, the EEG study. And so one can look at two-way dependencies as between different parts of the brain in the EEG, of course, is measuring surface electrode potentials as maybe a way to get insight into the effect of alcoholism on brain activity. And so I just show here, this is applying the Glasso, the raw data. We have 61 electrodes, 128 time points, 30 different trials to estimate the empirical statistics. We chose a regularization that was motivated by the theorem that I just presented. And then we found that with control subjects and alcoholic subjects, that there are apparent differences in the inverse covariance. So these are the conditional dependencies. The frontal lobe and the parietal lobe are quite a bit more disconnected in the alcoholic subjects than they are in the control subjects. If you look at the overall connectivity within these different lobes, there's some loss in connectivity. This is all with cross-validation of the regularization parameters. Look at the temporal component of the decomposition, the A component, right, in the Glasso. And you can see that comparing for control and alcoholic, both of the groups appear to have this pretty strong stationarity structure, right? It's not quite toplets, but except for these sort of periodic dependencies that appear, we have a pretty consistent kind of presence of dependency across time. These are interrupted from time to time, and these are likely due to the interruptions due to the protocol, the experimental protocol, where they're showing images, and then there's a rest period. But important to note is that the alcoholic group seems to have strong fourth order dependency. Now, both have strong second order dependency. So this is the second order statistic, second order lag. And that implies that that there's oscillatory behavior, right? There's like it's a second order recurrent equation that describes an autoregressive process that has this type of would have this type of banded autocorrelation viewed as in matrix form. So there's an oscillatory process in this data that both alcoholic and control subjects appear to have, but the alcoholic subjects also appear to have this higher order sort of non-Markovian or long-range dependency in perhaps due to memory issues or who knows what. This sort of riffing on some of the possible speculation here. So the conclusion is that these Kronecker representations are very powerful, and they can be used in various ways. The Sparse Kronecker-product models have been very successful in the past, and they've been studied and made into R routines that can be applied to a variety of different applications that have this natural multi-way structure. If you're looking for scalability, sparse Kronecker sum models are much more scalable because of their convexity and fast algorithms that take advantage of that convexity for estimating inverse covariance. And then if you're looking for an interpretable model, which the sparse Kronecker sum is not, then these Sig-Lasso squared sparse Kronecker sum models for the inverse covariance are worth considering. So all of this is discussed in the papers I showed you in the first or the second slide, and there's code for these methods that's also available. So with that, I think I will stop and ask if there are any questions or comments. Be glad to try and answer those.
Great. Thank you very much, Al, for the presentation. Sure, we'll open the floor for questions. So remember, you can use the Q&A chat, but in the case of Venom, we'll just unmute you. Yes, Venom, go ahead.
Oh, I love the reference to Breckenridge, by the way.
Yeah.
Now, when you talk about you talked a lot about inverse covariance matrix, and when you talk about that, my mind immediately goes to Kramer-Rauer lower bound, right?
Yeah, right.
And now, is there any sort of relevance or intuition from that in some of these analyses?
Yeah, there is, because the reason that the Kramer-Rauer lower bound depends on the inverse covariance is because that is, in fact, the natural parameter that limits performance, right? So it's really the conditional dependencies in the inverse covariance that are important in being able to tease out dependencies, and it's not the dependency structure itself. And the reason is that the inverse covariance is induces the natural factorization under a sparse assumption on inverse covariance of the multivariate log likelihood, or the likelihood, the additive property of the log likelihood. So the CRB is basically sort of capturing this natural description of factorization of conditional independencies that can be and should be taken advantage of by maximum likelihood estimates or other efficient, asymptotically efficient estimates that the CRB, of course, becomes achievable for. So there's a very close connection, and that is because the inverse covariance is the natural parameter for the multivariate Gaussian family.
Thanks.
Yep.
Good. Any additional questions from the audience? I know that we are already over 2 p.m., but we can continue discussing a bit with whoever can stay. So let me actually kick. Maybe I can go with one of those. So you know, in Tera Lasso, you showed this theoretical result that kind of depended on that mean or max MK, right? So you had this decrease in the needed sample complexity. I missed that, but in the Sylvester, right? So do you get indeed something like that, or with that specific dependence, or
it's not as simple? Yeah, it's not as simple. Yeah. So yeah, the Sylvester, we can tease out the conditions under which we get convergence, but we get this sandwiching of the Frobenius norm. But identifying this MK, I think it appears. I can't recall exactly where, but I think it does appear in the constant, but we don't have a direct comparison yet
right.
in terms of where we get additional improvement, and it's actually not clear. And in fact, I think it's much more complicated because of the fact that this Sig-Lasso is a combination, if you like, of Kronedker-product and Kronedker sum.
Yes.
My guess is it's going to be a much more complicated story than just a single scalar quantity that gives you an improvement factor.
Mm-hmm. And then and for Tera Lasso, like if you look at the actual like the actual dependence in practice, do you see this like 1 over square root of MK appearing like in practice, or is this bound to lose?
Yeah, that's a great question. Yeah, so we've looked at the bounds more as a way to evaluate how to choose the regularization parameters.
Right.
How do you scale those as n gets large and d gets large? In terms of the tightness, we don't think that these are the tightest bounds available. I think that's because we're using for Tera Lasso, for example, we use some concentration inequalities, but that these have conditions under which they're tight, and those conditions depend on certain asymptotic limits, and those asymptotic limits you can never replicate them in terms of a simulation. So the short answer to your question is that we haven't actually looked at that closely. The tightness, and it's an interesting question given the amount of effort necessary to even get these bounds. To get tighter bounds might even be more more difficult. But on the other hand, they might already be tight. And so that's why it's worthwhile doing what you're discussing.
Okay. Let's see. Is there any closing question? I know it's 2:10 already. I see that Rich is just a great talk, and he'll speak to you in a while.
Great.
I actually have maybe some additional things, but I will also be speaking with you in a second. So
right.
So I want to give the rest of the audience if there's any last minute thing. Okay.
Thank you, everybody.
Yeah, thank you, of course, Al, for joining, and thank you everyone for joining as well. Remember that this talk is going to be is recorded and will be uploaded to our YouTube channel, so you can watch later, or let people that could not make it today let them know that they can watch it over there. Thank you very much, and Al, it's a different Zoom link that I'll see you in a bit.
That's right. Yes. Okay. See you in a bit. Yes.
Thank you. Bye bye.